Hello. Hey, there I am. Testing, testing. Good afternoon. How's everyone doing, huh? Woohoo. All right. Um, all right. So, good afternoon, everyone. How's everybody doing? Oh, I forgot to say that we're going live. We are live, everyone. Choo-hoo. Okie dokie. So, where am I? Yes, and my phone says we're going live too. So I think we're good. We're ready to start. Oh no, we're not ready to start. I need to set up my drawing gear, which I always forget. So I'm going to bring in, and my lighting. Oh, well, are you going to see me in my pajamas today? I am not in my pajamas, but could have been, because I spend a lot of time in my apartment these days. Oh, oh my God, what am I doing? What am I going to destroy here? Oh, totally gonna break something today. Woohoo! Hey, Salvador, good afternoon. Oh man, you're really joining the live stream. You're really doing the live stream thon, huh? That is so awesome. I'm really thankful. Thank you, Salvador. Big thumbs up for you. Also, I saw your post on Discord. I'm gonna give that some thought because those were actually pretty interesting. Those were actually pretty interesting examples. So, right. So I'm going to connect to a wireless display. And I think I am here. Am I here? Yes. All right. So I'm going to put this in here. And my drawing. And let's see if we are ready for this here. And this has to go right there. And then you should see me. Oh, I forgot. Hi. All right. Wait. Let me do. This is parametric camp. Woohoo! Boop, boop. Oh, wait. No, wait. More like. Oops. Oh, wait, and I have this toolbar in the middle. Alrighty. I like the, oh, that C is kind of clunky. Whoop. All right. I like this. Aha, this is parametric cam. Welcome. Much better, right? Hey, Mohammed, what's up? Alrighty, and a little bit here. Yeah. All right. I don't know what happened here, but I'm actually going to save this. Because why not? Well, so sketching is working. That was the bottom line. All right. So, how are we doing? How is everyone doing? Thanks to you, Salvador, and thanks to everyone who joins us relentlessly, sunny or cloudy or snowy or windy, every day when we do live streams and we talk about computational design. We learn new things, we write code, we generate cool forms, nice graphics, and all those things that we like doing in this channel. My name is Jose Luis. If you're new to the channel, I run this thing called Parametric Camp, aka P Camp, as we call it in the, on the streets. And we do live streams. We record live tutorials that we then chop and trim and edit and publish a bit more polished. And if you want to be up to date with what we're doing, you can follow us on social media. You may want to consider subscribing to this channel, liking this video, hitting notifications so that in your phone it pops up that when do we stream. And like on my phone, you see, my phone is telling me that we're live, which is a very good sign. And we also have a Discord server, which I'm going to post the link for here. We use that server to have offline conversations throughout the week. And we have a bunch of channels where we post questions, we have conversations, people help each other. It's a really nice community, and it gives me the opportunity to get to know who you are. So if you join the channel, if you join the community, please make sure to go to the introductions channel and say a little bit about yourself. We have a template that you can use if you wanna just like a few cues about what can you say and how can you introduce yourself. And also we have a Google Calendar that you can subscribe to that has the events of when do we go live. This week, as you may already know, we are doing a bit of a special week because we typically stream on Fridays, but this week we're streaming every day twice, so that I can wrap up, which it looks like I'm not going to be wrapping it up, but so that we can wrap up this playlist that I have called, that I'm working on, that is called Introduction to Parametric Modeling. So I'm really excited about making this happen. And if I have to extend this into next week, I might actually do it, because I really, really want to make this happen. And this is live stream. Which live stream is this? 56, which is great because it was my New Year's resolution this year to hit 100 live streams by December 31st. So we are not at a good pace. We're not, we have to work, but slowly, it's happening. It's happening. So, Dusko and NT, good to see you back. So what are we doing today? We are continuing with the list, Introduction to Parametric Modeling, and today the topics are going to be, we finished data structures, we talk about data, grafting, blah, blah, blah. And we made a small freeform pavilion exercise. And then what we're going to do today is we're going to go back to geometry stuff. And now we're going to talk about vectors. We're going to talk about planes. We're going to talk about doing numerical series. And we are going to talk about Euclidean transformations. And after that, hopefully, we're going to make a bunch of cool exercises. We are going to do a bunch of cool exercises, but do we need to do do we need to wait to do all of them, or can we insert them? I wonder if instead of just like I have here doing all the vectors, we can wait for planes. I think we can do this. Yeah, let's just do it all together, and then we do a bunch of exercises that just aggregate all the stuff together. So what are we going to do? What are we going to do today? We're going to do a lot of stuff. We're going to do vectors, we're going to do planes, we're going to do numerical series and domains, and let's see where we get with that. Shall we get started? Any questions, concerns, suggestions? You can throw them at me here. You can also always throw them on the Discord channel, of course, on the Discord server. I always call it channel, but it's a server. I need to remember that. All right. So how are we going to start this today? So the first thing we're going to do is we're going to talk about vectors. We're going to talk about vectors. And in order to talk about vectors, I would like to do, what am I going to do? I'm going to explain that they are, I probably want to start with the sketchboard. We're going to explain that they are basically units of information that contain 3 numbers, and we can talk about how vectors are interchangeable. And I probably want to do that with some sketching here on the board. I probably want to do that with some sketching, and then what are we going to do? I want to do some grasshopper examples, and I'm going to do a few operations. Yes, okay. And so let me fire up Rhino to start with. We're going to start that. I'm going to start this. Hey, Dong Yoon, how are you doing, sir? Good to see you. It has been a while. Are you enjoying your summer? Dong Yoon here on the chat is actually a friend of mine. He's my student at Harvard, and I believe he just wrapped up the semester and he's ready to do something in the summer. Just shoot me an email. I don't really know what you're doing this summer. Let's shoot me an email and let's catch up or something. Alrighty. So, hey Andrés, hola, ¿cómo andas? So, all right, vectors, and we're going to do vectors, and what do I do? Do I have an introduction? I have an introduction. Well, let me draw some. I'm kind of excited about this thing. I'm kind of excited about this. Yeah. This brush, which is kind of bad, but it's a little too much, right? Anyway, it doesn't matter. It's my thing now. I'm using this brush. Okay. So I will do that, and then I'll probably say today we're going to talk about vectors. And yay, sure. No, sorry. That should go on the other layer. It should go on. All right. Okay, vectors, no exclamation mark. Okay, so, and then I'm just going to start the video. And then after I do that, I probably want to switch to, okay. All right. Okay, so let's just start. And if I have to repeat, I'll just get over it. I'll just do it again. Okay, let's do this. Hi, this is Jose Luis, and welcome to another video on the series Introduction to Parametric Modeling. I think this is going to be the video of a new section where in the previous videos we were talking about data manipulation and simple forms of geometry. I think in this video, I would like to tap a little bit more on some of the aspects that, what do I want to do? Not, we're doing it again. So what do I want to do? What is this section about? Is it about the algebra of modeling? Because we're going to be doing planes, vectors, then numerical series and Euclidean transformations. That is basically what would be a common name for all of those? Mm. Mm-hmm. It's not nerves. Nothing that we're going to see is nerves. It's basically, it's mostly vector algebra in a way. But I don't want to call it vector algebra because it sounds scary. What should I call a section that is going to do vectors, planes, numerical series, and transformations. So Euclidean transformations like rotate, escalate, scale, those things. What should I call that? What should I call that? I don't know. Let's see. Should I Google this? Is this what I'm doing? Vectors, planes, transformations, vector matrix and coordinate transformations, linear transformations, transformations and coordinate, translation vectors, content, geometry, vectors and transformations in plane geometry. What is this book? This is cool. Okay. All right, so I don't know how I'm going to call this, so I'm just going to call it the entities that make, the simpler entities that make geometry generation and manipulation, the algebra. I maybe use the word algebra. Why not? I mean, it's scary, but we're trying to become pros here, so why not? Let's do that. Yeah, let's do that. All right, let's go. Hi, this is Jose Luis, and welcome to another video on this series, the Introduction to Parametric Modeling. In this video, I would like to start a new section because in the previous videos, we've talked about nerves geometry and surfaces and curves and all those perhaps like more complicated things, but we actually kind of tiptoed over some even more basic geometry entities that are fundamental to the generation and the manipulation of geometry in general. And so in this overall section, in this group of videos, I would like to talk about vector algebra in general, and I would like to talk about simpler forms of geometry such as points, vectors, planes, numerical series, and transformations, so that we can really grasp down the numerical representations that there are. No. We're starting over again. I was not liking that. Let's start over again. Hi, this is Jose Luis, and welcome to another video in this series, Introduction to Parametric Modeling. In the previous videos, we have talked a lot about nerve geometry and curves and surfaces and all this, like the polynomial mathematical representation, blah, 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 like complex stuff. But we've actually kind of tiptoed over more simple, fundamental forms of geometry that are at the core of all the geometry generations and all the geometry manipulation operations that we will be doing in parametric modeling. So I would like to take some time in this overall section in the next few videos to really take a closer look at simpler geometrical entities such as vector planes, numerical series, and operations such as Euclidean transformations, so that we can have a really good hold on how they can be used numerically to generate and to manipulate geometry, and therefore make us stronger in the fundamental tools of computational geometry. So in this video, I would like to start with probably one of my favorite subjects, which is vectors. And I would like to take a close look at what vectors are, how they're different from other entities, and how we can use them for our advantage. Okay, so I did like that. So we're going to stick to that one. We're going to keep that one, and then what is the next thing that I'm going to do? I'm going to start explaining what vectors are. And for that, can I draw? Yes, so I can draw here. So, okay, so I'm going to start. Vectors are typically represented as an arrow. And I will want to write that they have direction, orientation, and magnitude. I may want to write that somewhere here. So vectors have the direction, orientation, they have direction, and they have magnitude slash length. Actually, I'm not liking that. This, and this. Oh no, very good, nothing. Okay, and that is going to be here. So I'm going to draw arrows here on the right hand side. Okay. So what are vectors? Well, vectors are typically represented as an arrow. So they're typically represented as an arrow, something like this. Okay. And what does that mean? It means that as opposed to, for example, points, which are entities that have a location, that represent a location in three-dimensional space, what vectors represent is a direction and an orientation in three-dimensional space, including a length. So we're starting over. We're starting over. Okay, so all right, so we're starting over. So what are vectors? Well, vectors are typically represented as an arrow in textbooks, and as you will see in Grasshopper as well. And they're represented as an arrow because, as opposed to points, which represent the location of some location in three-dimensional space, vectors, what they represent is some kind of direction or an orientation in three-dimensional space, as well as a length. But what they do not... Starting over. So what are vectors? Vectors are typically represented in textbooks and in in modeling environments. They're typically represented as arrows. And they're represented as arrows because, as opposed to, for example, points, which are typically used to represent location in three-dimensional space, vectors are entities that represent three things. They represent an orientation in three-dimensional space, so they have some kind of angle in 3D space. They represent a direction, so not just the angle, but whether if they're pointing in one way or the other is also important. And then they also represent a magnitude or represent a length. So the same orientation and direction can be stronger or can be weaker. All right. But what they do not represent, and this is very important for us to understand, is they do not represent location in 3D space. Okay? That's what points are meant for. And the idea is that this vector that I've drawn here, for example, would be the same as this one, would be the same as this one, and would be the same as this one, but it would be different from this one, or from this one, or from this one. These would be vectors that are not equivalent. So a vector is simply a magnitude in three-dimensional space that is pointing in some direction with some kind of strength, but can be represented in any place in three-dimensional space. That doesn't matter. Vectors are very commonly used to represent orientation and direction. They're very common, for example, in force fields. They're really common, for example, when we work with magnetism, electromagnetism. And they're also super, super important when we are working in computer graphics, for the reasons that I will explain very soon. And the way vectors are typically represented numerically is with the following. They're typically represented with a set of three numbers, for example, in three-dimensional space, like, for example, 3, 5, and -2. Let's imagine that those are, right? Those three numbers represent the x and y and z values of the orientation of the tip. All right. And this kind of representation assumes that if you start, let's say, if this vector was to start at the world coordinate 0, 0, 0, then the tip of this arrow would be located in coordinates 3, 5, -2. That doesn't mean that the vector has to be in coordinates 0, 0, 0. It means that if it were where it started, then the tip would end in that point. So, for example, let me give you another example. Let's say we had 2 points, we had a vector between them, and then the coordinates of this point are 2, 4, 5, right? And then the coordinates of this point are 3, 4, and 5. Could you tell me what is the numerical representation of this vector? Well, because these points, they have the same x and y, they have the same y and z, the 2 points, then it turns out that this vector, the only... am I messing this up? I am messing this up. Rewind. What did went wrong here? Okay, so let me just start over again. Where is my mouse? Okay. Okay. And how do we represent vectors numerically? Well, it's actually quite easy. Imagine that we had, for example, this vector, and the starting point of this vector was the world coordinate 0, 0, 0. If that was the case, that doesn't mean that the vector has to start from there. They don't have location, again, intrinsically. But if that was the convention that we used to represent this vector, then wherever the coordinates of where the tip of this vector would end, that would be the numerical representation of this vector. So for example, let's say that this vector ended in coordinates 2, 3, and 5, and -3. If that was the case, then oh my God, why is this so difficult? How about I think through what I want to say, and then we start it over. We do it. Okay. I think I was liking the way I said it before. So I want to say that vectors are represented with 3 numbers, and that's those numbers. What they mean is, if the vector was in 0, 0, then that's where the tip would end. So, but that doesn't have to be the case. And then I'm going to draw the other example. Let's say I have a point and I have a vector that is 0, 0, 1. So where does the tip of that vector end? So it ends in, okay. So let's do that. And how do we represent numerically vectors? Well, it's actually quite easy. So vectors are typically represented with 3 numbers. Let's say, for example, 2, 5, and -3. Okay? And those 3 numbers correspond to imagining that the vector was starting from coordinates 0, 0, 0, from the world, from the origin of coordinates. If that was where the vector started, which again, it doesn't have to be there because vectors don't have location, but if that was the case, then these 3 numbers would represent the coordinates of the point where the tip of the arrow would end. Or if you want to or if this is easier for you to understand in this way, the x and y and z location coordinates represent the length of the vector in the projection of x, the length of the vector in the projection of y, and the length of the vector in the projection of z. Whatever resonates better with you. So, for instance, for example, if we had a point that was in coordinates, I'm going to say, I don't know, 3, 7, and 2, all right? And then we had a vector such as this, and the vector was a vector 2, 0, 0, all right? That vector is not really located in the origin. It doesn't really have a location, but what would be the coordinates of the point at the tip of the arrow in this case? Well, it would be whatever the coordinates of the original point were plus the coordinates of the vector. So this point here would be on coordinates 5, 7, and 2. All right? But the vector can be used interchangeably anywhere. Okay, I think I'm going to keep that one. Now, what do I do now? I think at this point we're ready to start going to Grasshopper and start taking a look at how to create them and how to manipulate them, right? Mm-hmm. Mm-hmm. Wonderful. So shall we go back to Grasshopper and then take a look at how vectors are created and handled in the software? Let's go take a look. All right. I'm a little all over the place today with this one. So what are we going to start doing? Okay, so I'm going to plug in, I'm going to drop in a bunch of unit vectors, and I'm going to and then I'm going to create a vector from XYZ coordinates, and I'm going to show it in 3D space. Okay. Inside of Grasshopper, all of the vector operations are actually found under the vector tab. And there's a bunch of categories. There's grid, there's planes, points, which we will see very soon. And most of them are actually here on the vector category. So the simplest forms of vectors that I can think of are unit vectors, for example, in the x direction, are unit vectors in the y direction, or are unit vectors in the z direction. And if I plug in a panel here, you can see that this is a vector of the form 1, 0, 0. So 1 unit in the x direction, this will be 1 unit in the y direction, and this will be 1 unit in the z direction. If you notice also, Grasshopper is very smart in dropping the components here already without any pre-visualization. And if I turn it on, I can't really turn the visualization on. It just doesn't work because vectors on their own can actually not be visualized. They have to, they cannot be visualized on their own because they don't have a location in three-dimensional space. So the way I can visualize vectors is, for example, by going to the display tab here and going to vector and using vector display on vector display extended. So I'm going to use the simple one, vector display. I'm going to place this here, and I'm going to see that the inputs, it asks me for the vector that I want to preview, that's V, and then it asks me for an anchor point to preview the vector, which is kind of interesting because I have to artificially tell it where I want the vector to start. And with that additional information, then Grasshopper can actually show me that vector somewhere. And you can also notice that this component is a little special because it doesn't have outputs. The only thing that it does is it shows up stuff visually on the canvas. So for example, I can try to visualize the X component. And what I'm going to do, I'm just going to drop a point here. I'm going to bring that point into Grasshopper, and then I'm going to use it as the anchor. And you can see that as I zoom in here, you can see that I have a point that is a vector that is represented on top of this point. Or if I were to, for example, just drop a radial grill, a radial grid here, you could see that if I plug all of these points here, I can have all of these, I can have all of those vectors represented on top of the points of my radial grid, for example. And that can be unit X, that can be unit Y, or those can be unit Z in the Z direction. That's kind of cool, actually, huh? All right, so another thing that I can do is I don't want to delete that point. I want to bring it here. So another thing that I can do is I can generate vectors numerically through their x, y, z components. So for example, I'm going to create here a vector x, y, z, and I'm going to give it, for example, I'm going to say 10.00, and then that's going to be x component, y component, and z component. And you can see that if I now pre-visualize that vector on the point that I'm bringing in from Rhino, you can see that that vector now has no z and no y. It's just a pure x vector, and it's longer and shorter, and now it has some y component, and now it has some z component. Does this make sense? Or, for example, one of the most popular ways of creating a vector, and let's take a look at what this vector looks like numerically. So that's going to be here, that's going to be this vector with the coordinates 220, 289, and 3, blah, blah, blah. As you can see, neither of these 2 points is in these coordinates. These coordinates are the coordinates of the vector if it was placed in 0, 0, 0. Another really useful way of creating vectors is creating a vector between 2 points. This is a really, really common way of doing this. So for example, I can create a vector between 2 points, and I took one here. I could create the other one, but I'm just going to do it manually in Rhino. I'm going to bring this point here, and then I'm going to say I want to vector from A to B. And then I want to visualize that vector. And you can see that the vector is now going from one point to the other. All right. And what is the numerical representation of that point? Is all this decimal stuff here. What is so interesting about this? It's so interesting because since the point, the vector, are the coordinates of the difference, the vector has the coordinates of the difference between the x and y and z coordinates of each one of these 2 points. Because if you imagine, if we moved this from here to 0, then you can see how the coordinates of this vector are actually the same as the coordinates of this point here. But if I move them all together, then the vector is representing the differences in coordinates between the 2 points, which is also pretty interesting. I can also generate a family of vectors between 1 point and multiple points. So let's go back to, let's drop here another grid, for example, and then let's move this point all the way up here. If I move this point here, and this plane is kind of confusing a little bit, so let me just stick to the point. So I'm going to use the points here, and I'm going to turn off the visualization of the grid. If I create a vector, and I'm going to turn this, if I create a vector between 2 points, right? And the first one is the point that I have here on the top, and the other one is the points that I have on the grid, then what I can see now is that I have a collection of all the vectors that go from point A to each one of the points on the grid. And if I visualize that, you can see that I have a nice display of projections from this one vector to the others. All right? But that is if I choose to represent these vectors starting from point A. But that doesn't have to be the case. I can choose to represent those vectors starting from the other point that I had manually here. So for example, this one here. So all these vectors are now the same vectors. They're just projecting out from this other point. Or how about to project these vectors out from each one of the points on the grid? So I'm going to take the points of the grid and I'm going to use those for anchors for each one of the vectors. So now with this, it kind of looks like this point here is kind of projecting shadows on top of each one of these points, which correspond to the distance of the point to each one of the other points on the grid, which is kind of cool. So these kind of vectors now could be really useful to project shadows, to do sun analysis, to do reflections, or to do, for example, attraction and repulsion, to push those points out or inside. You know, that could also be a really interesting application. There's even more stuff we can do. So for example, let me draw just some curve here like this, and I'm actually going to click on the the control points so that I'm going to give it some volume so that it's more, so that it's not a planar curve, it's like it's in 3D. Okay, so we have this curve in 3 dimensions here, and I'm going to bring that curve inside of Rhino. Okay, now I have that curve, and what I'm going to do is I'm going to subdivide this curve into equal length segments. And we've done this operation in many exercises before. I'm going to do, for example, 20 subdivisions, whatever. All right. And then typically what we were interested in were the points that we were subdividing on. But it turns out that, as we said before, the component gives us points at those divisions, but it also gives us the tangent vectors at those divisions points, which is actually super interesting. So let me see if I can, for example, let's say that I'm going to now take, this vector display, and what I'm going to do is I'm going to visualize all these vectors, all right? And the anchor points that I'm going to choose for all these vectors are going to be the points on the curve. So if I do that, you can see that super interestingly, what I'm getting is the vectors on the curve that represent the tangency in 3-dimensional space of the curve at that point. This could be super, super useful if we wanted to, for example, make some operation where we place geometry on top of the curve, and we want to make sure that that geometry is oriented in the direction of the tangency of the curve at that point. Super, super interesting. I have a problem though. It feels like the vectors are kind of small. I can't really see them well in this graphic. Why is that? Let me place a panel here to look at the vectors, and it turns out all the coordinates are smaller than 1. This is because tangency on a curve is a property that, where the only thing that's important in that property is the orientation, is the direction of the vector. But how long that is, it's not important, it's not a property of the curve. And then Grasshopper chooses to give you vectors that are unitary, vectors that have a length of 1. How do I know that? Well, I actually know because I could go to vector and I could say, can you give me the length of each one of these vectors? And if I did that, oops, sorry, these are the vectors. And if I did that, you would see that each one of the vectors was vector with a unit of 1. If I go back to what I did before, which was the grid of vectors here, you can see that for these vectors, now each one of them has a length of whatever. Some are shorter, some are longer. But in the case of the tangency, turns out that all the vectors have a tangency and a length of 1. Okay? So I'm using the vector length component to read that information, but there's another vector called amplitude that I can use to change that value. So for example, what this vector component does is it takes a vector, it takes a length, and then it gives you back the same vector, but increase or decrease to match that length that we specified. So for example, I can say all these vectors, and I want them to be like super long, for example. Then what I can do is I can just modify all these vectors. Now these are the coordinates, and those are the vectors that I'm going to visualize now. And you can see that the vectors are longer, and I can increase them and decrease them, increase their lengths, or decrease their lengths. All right? How cool is this? And this technique that I am showing, the finding the tangency to this curve at points, is not only something that I can do on curves, but I can actually do something very, very similar with surfaces. So I have just created this one surface here with a little bit of undulation, and I'm going to bring that surface back here into Rhino. So for example, surface, I'm going to bring it here, etc. Right? And then what I'm going to do is I'm going to do a process that we have done before, which is to subdivide this surface into a grid of UV points. What that means is that I can subdivide that, okay? And then I can say, well, I want, for example, 15 subdivisions in one direction, and I want 15 in the other direction, so that I have a few more points. So if you remember, when we were looking at this component, we saw that the surface gave the component gave us the division points, so those that we can see here. But another thing that it gave us was the normal vectors on those points. Vectors that are perpendicular, exactly perpendicular to the surface on each one of those points. So those vectors can also be visualized using the display vector, the vector display. So if I visualize the vectors anchored on those points, you can see that, well, the way I have drawn the surface, it looks like the normals are sticking down, but you can see how all the arrows are pointing exactly perpendicularly in the direction of the normal to the surface. And because I can set the amplitude of those vectors, so I'm just going to say, for example, those vectors need to have a value of, for example, and I'm going to make this slider be able to be negative, and they can have a value of positive 10 all the way to minus 10, for example. And this way, I can visualize the direction of these vectors, the direction of the normals of the surface on top of these points. This is extremely useful when we want to have a freeform surface and we want to, for example, place objects on top of them that respect the orientation of the normal. This is a really common operation to do, and so finding the normals on a surface is a really useful technique, giving us a vector that then we can use to feed to other geometry processes. Yeah, no, this is not gonna work. Mm-hmm. Have this vector, which I'm displaying like this, right? Then I is to add two vectors. Add the two vectors. And then display that on top of A, on top of B. I wonder if I should just go a little farther away. Am I back? Yes. Okay. And these are going to the trash. And this is going to be trash. And I need to close my window because the sun is starting to hit me in the face. There you go. Okay, ducky. Well, that was bad. I don't know. I don't know where it got cut, so I'm just going to start over again. Oh, actually, let me just here. Is this the video? If you're ever doing project, it's like a dot product, but with the sign instead. Are you guys? Okay. All right. Hey, we're live. Look, how exciting. Okie dokie. All right. So let's go back. Sorry for that. Okay, now vectors have a super interesting algebra behind them of operations that we can do, and many of which are particular to vectors, to what's called vector algebra. Sorry to be redundant. We're not going to get very deep into those details in this video, but long story short, for example, if you want to know properties or you want to make simple manipulation of vectors without getting into the weeds of how that happened, you can access many of those operations here on the vector tab. So for example, you can calculate the angle between two vectors, you can calculate the length of a vector, which is actually done with the Pythagorean theorem, but here it's just done for you. You can rotate a vector around an axis, you can flip the direction of the vector, which is just simply changing the sign of the coordinates of that vector, and then you can do the dot product or the cross product. These two operations are fundamental to vector algebra, and they have really, really interesting properties of what they can give you and why. We're not going to get into any of those today. If you're interested in getting into the weeds of more detailed vector algebra, I highly recommend that you check my video on on the course that I teach at Harvard, Introduction to Computational Design, and the lecture where I talk specifically about vectors, all their properties, and the algebra behind them. It will hopefully pop up somewhere on the screen, or it will be in the description of this video. And if you're interested in general, you can also check the full playlist, which is all the lectures for the course. Now, I would like to show, for example, one of the simplest operations that we can do, which is adding two vectors together, which is actually not here because the way we do this is with the mathematical tab. All the operators, addition, multiplication, etc., all of those can actually, many of them can apply to vectors as well. So for example, here we have two vectors. If you remember, the one vector was the vector that I created from the first point and the second point, which if I display it on top of this point, it gives me this vector here. And the second vector was a vector that I just created straight from x, y, z coordinates. And if I plot it on top of the second point, you can see that it looks something like this. And from a coordinate standpoint, if I take a look at the numbers that define the first vector and the numbers that define the second one, they look something like that. All right. Well, turns out that I can add two vectors together for example, with the addition component in the operators, and then I can plug that one in, that second one in, and I can see the result, which if I add it to this panel, you can see, it's difficult to see, but more or less you can see that the x coordinate is the addition of the first two, the y coordinate is the addition of 7 plus 2, and the z coordinate is 3.9 minus 0.78 or something like that. All right, so addition is just simply adding the x coordinates together, the y coordinates together, and the z coordinates together. However, graphically or geometrically is a really interesting operation, because if I were to plot this vector that I just created on top of the first point, that is going to be this one here, you can see how the resulting vector, the addition, is basically putting one after the other and then joining the start point of the first one with the end point of the second one, which is a super interesting property and is extremely useful for doing a lot of operations like vector modification, moving points around, moving vectors. So it's a really basic and useful operation. Again, if you're interested in more details about vector operations and what they mean, make sure to check this lecture if you have the time and you're interested. Okay? Mm. In the same spirit, I would like to highlight another super interesting property of vectors, and this time in relation to points, for example, and it is the fact that if you think about this carefully, vectors are represented by three numbers, whereas points are also represented by three numbers, which means that at the end of the day, both are just three numbers. And the only thing that makes them different is how we, computationally or geometrically, how we interpret them. So one of them, we think of it as location in 3D space. The other one, we think of it as an arrow pointing in a particular direction with a particular magnitude. But in a way, since they're just three numbers, for the computer is the exact same thing. And therefore, a lot of the algebra is shared between the two. And in a way, they can be used interchangeably between each other. So for example, wherever I can plug in a point, I will be able to plug in a vector, because basically the three coordinates of the vector will be taken as a location in 3D space, and vice versa. But at the same time, I can also operate with them between each other. So for example, if I have a point in three-dimensional space and I have this one vector that I have defined using three numbers, I can represent the vector just by plotting that vector anchored on that original point. But it turns out that if I add these two objects together, if I take the point and I add, let me actually plug a panel so that we can see these two. The point is 3 coordinates, which fortunately they don't show up here. And the other one is 3 coordinates as well. Turns out that if I add the two together, then what happens is that the coordinates of one get added to the coordinates of the second one. And what happens is that this point, now instead of being in the coordinates that it was, it has new coordinates, which are the original ones plus the x, y, and z coordinates of the vector. And therefore, I have a new point that is at the tip of the vector that I located at the original point. So in a way, adding a point and a vector, graphically and geometrically, what it means is moving the original point, but in a direction and with a magnitude that is equal to the vector that I am adding to it. So a point and a vector added together is just the same as moving, is kind of the same as moving a point in three-dimensional space, which is also a super, super interesting property that we will use really, really extensively. Okay? All right, well, so this was vectors in a nutshell. As you can see, there's actually a lot of depth in when it comes to doing vector algebra and vector operations, but I would like to put a pin on that one before we get into the nitty-gritties. But again, if you are called to learning more about that, I highly recommend you check my lecture where you can see a breakdown of like the properties of the dot product, the cross product, and why it's interesting and what do you get, etc., and the geometrical and numerical relationships. But otherwise, if maybe we're not there yet, if we're beginning, so perhaps what we can do is we can learn more about how vectors can be really useful for us, just doing some practice exercises farther down in this series of videos, okay? Which is what we're going to do. So this is going to be vectors for the time being. We're going to see them. They're going to come back all the time in all the videos that we're going to see. And I think we're ready to move on to the next topic, which I think is going to be planes. So if you think you like this video, maybe consider hitting the like button, hitting subscribe if you want to learn more, turning on notifications to see when we go live, when we publish videos. And in the meantime, hopefully see you on the next video. Thanks a lot. Hey Anish, what took you so long to discover this channel? It's amazing. We like it a lot. Alrighty. Okay, so that was vectors. Was that clear? Do you think I made a good case? I don't really know how to talk about these things in a fast way. I'm always torn between doing it fast and just doing it quick, or if I want to like really hone in and learn, or if I want to really like, because like I'm always like torn between doing it quick and easy, quick and dirty, or like really delving into this, which because if I do, then the whole playlist is going to be like, I don't know, 27 hours long, which is kind of bad. A niche, computational design and vector algebra is extremely relevant to structural engineering. You're going to learn a lot. I mean, vectors are basically forces. Forces are basically vectors. So this would be super helpful if you want to get better if you want to get better at doing that. Yes. All right, so now what is the next thing we're going to do? We're going to talk about planes. And how are we going to do that? I'm going to save this, which I already did. I'm going to save that, and then I'm going to create a new one, and I'm going to use my new favorite brush, which is this one. Alrighty. So planes, what are planes going to be? Planes are going to be defined by the following. They are typically a point in 3D space, then they are an arrow, a vector in the x direction, and they are a vector in the y direction. Okay? And by doing this, what they do is that they form this kind of two-dimensional plane that is very useful for everything, basically. We're working on that right now, Anish. We're actually completing that list right now. So this is what we're doing this week, basically. And so that's that. And the properties is that this is a unit vector. There's a unit vector. Wow, it's really difficult to write small on this screen. What if I did this? And this one is also a unit vector. And then the angle between these two is 90 degrees. All right. Okay, so and so and there's something implied, which is that there's like a third vector. There's a third vector which is C. My God, what is going on? There you go. All right. Okay. Oh, I didn't save this. Wait. So this is going to be 6.1. What is this? This is going to be 6.1 vectors, and this is also going to be 6.1 vectors. All right, and then it's going to be a new one. And yes, I want to save. And then a new one with no template. Okay. So now let's take a look at planes. All right. How's everyone doing today? Anish, you haven't heard me, but please go back to the beginning of the video where I explained that we have a Discord server and we have social media and we have a lot of things that could be useful for you to catch up on what we're working on. Okay? Thanks a lot. Now let's go back to planes, which we're going to do start from here. Okay? All right. Hi, this is Jose Luis, and welcome to another video on the series Introduction to Parametric Modeling. In this video, we were just talking about vectors right now. In this video, I would like to introduce another geometry entity that is very, very often super useful for a lot of things that relate to orientation in three-dimensional space, which is going to be planes. To-do! Planes! And what are planes? Well, if think about, we were talking about vectors. We described vectors as opposed to points as vectors having direction and orientation and magnitude in 3D space, and points having location. Well, imagine planes as being a combination of points and planes together. Why am I not just like cutting to defining what is, why am I making it more difficult? Huh? Okay, let's start over again. I'm sorry for the back and forth, but I really want to nail this playlist. I would like to make it quite lean. So, vectors, planes. Hi, this is Jose Luis, and welcome to another video on this series, Introduction to Parametric Modeling. In the previous video, we took a look at vectors, as we took a look at the algebra behind vectors, and we could already see how they were super interesting for basic orientation and translation operations, right? However, in this video, I would like to take a closer look at other geometry entity that is very common in a lot of the 3D modeling environments that I work with, which is going to be planes. And planes are extremely useful when it comes to orienting and locating three-dimensional things in space. And it is so because planes are actually an aggregate of three different things. A plane is made up of a center point. So the plane has an origin, it has a center, and that center is located somewhere in three-dimensional space. And then it has two vectors. It has a main vector in the x direction that is pointing to what is the main orientation of that plane. And it has another vector called typically the y vector of the plane, which is pointing to the secondary direction of that plane. All right? And what happens is that the aggregation of these three entities, a point marking the center, the origin of a plane, and then two x and y vectors, local x and y vectors, defining the orientation of that plane in three-dimensional space. What those three objects together do is that they form a two-dimensional plane that can have any orientation and any origin in world coordinates, and that is extremely useful to define orientation of things or targets of things or how to orient things in 3D space, or for robotics, for example, they're super useful to define a target for a particular motion operation. So they're super useful. Now, I would like to say that the way planes are treated in different software environments is different. Some software environments have planes that don't really have a center because they're closer to mathematical planes, which is a completely different story. Whereas other environments do have planes that have a center, and sometimes those are referred to as frames. So frames and planes are kind of interchangeable terms that you will find in different environments or different software packages. And in the case of Grasshopper, planes have a center, they have two main vectors, and those vectors have very particular properties. Those properties are that the x vector is typically an unit vector in any direction, and the y vector is also a unit direction, and it's also, sorry, it's also a unit vector. So both are unit vectors. And another thing that is mandatory in the case of Grasshopper is that the two vectors are perpendicular to each other. They are orthogonal. Or in another, or saying it in a different way, they form 90 degrees between each other. So if you think about this particular convention, what it means is that the two vectors form an orthonormal coordinate system. What that means is that the two vectors, because they're unit and they're perpendicular, they're actually very, very similar to the vectors that we use to represent the world coordinate. And therefore, this plane could be considered a local coordinate system. And it can be considered a local coordinate system also because if the two vectors are unit and they form 90 degrees between each other, then we can actually infer, we can actually deduce, doing a little bit of vector algebra, we could find a third piece of information for this plane, which is a perpendicular, a normal vector to that plane, which is typically referred to as the C vector. And if we represent it as a unit vector, then those three vectors together can represent a local coordinate system. Local coordinate systems are extremely useful. I can't even start describing like all the different ways we can use them. And if you ask me, for me, they are the MVP, the most valuable players when it comes to doing serious computational geometry. So we're going to see a lot of applications of this, and very soon I will try to start discouraging you from using simple points or simple vectors in general, and just stick to using planes as a general rule of thumb, as a general good practice. Okay, and that is because planes, since at the end of the day, they are defined by a center and two vectors, they're basically 9 numbers. That's what's important about them. And with 9 numbers, that is something super lightweight for the computer to process. We can actually get a lot of information and a lot of utility from it. So let's take a look in Grasshopper how planes are handled and how we can operate and how we can use them in different ways. Okie dokie, let's go to Grasshopper and place some bifocals here. Oh, I forgot to remove the bifocals from here. Okay, yes. Okay, and then so I'm going to say, okay, I'm going to throw here 3 sliders. I'm going to throw 3 sliders here. Okay. Let's start. So, as I said in my previous video, I believe planes and all the components that relate to plane generation and plane manipulation are also inside of the vector tab. The vector tab has basically everything that is cool in Grasshopper. So if we go to the plane category, you can see that there's a lot of different ways of creating planes and modifying planes. So for example, the most canonical planes, or some of the most useful one, will be the XY plane. The XY plane is a plane that that is typically centered on the origin, on 0, 0, and has the orientation of the X and Y. So basically, it's a plane that has the same orientation as the world coordinate. And if I turn the world coordinate off, if I turn the world grid off, you can see that the visualization in Grasshopper is this tiny grid, this tiny 4x4 grid, this tiny point here marking the center, and then a thicker red line marking the X direction, and a thicker green line marking the the Y direction. The Z direction is not showcased in the preview because it's implicit, because we can imagine the Z vector sticking out of here. I can also do, for example, a YZ plane. So for example, that will be a vector that will have its local X coordinate pointing in the Y direction and its local Y coordinate pointing in the Z direction. Sorry, the axis. The local X axis pointing in the Y direction and the local Y axis pointing in the Z direction. And if I turn that off, I can also use an XZ plane. An XZ plane will be a plane where the plane's X-axis is pointing in the global X direction and the plane's Y-axis is pointing in the Z direction. You can see that these three planes together kind of form this sort of I don't know, triplet of planes that define Cartesian space, if you will. Now, why are planes useful? Well, planes are useful because basically every component in Grasshopper that generates geometry, it doesn't ask you for a for a point. It asks you for a plane because planes can represent orientation in 3D space. And we have seen this in previous examples. So for example, if I go to curves and primitives, if I drop in an ellipse that can be defined by 2 radii, right? So what the ellipse is asking me is a base plane, because depending on the plane that I will give it, for example, and let's say that X is going to be this and Y is going to be this, right? Depending on which plane do I give it, then the ellipse is going to be in XY, is going to be in YZ, or is going to be in XZ, as you can see here, right? So if I now wanted to create, for example, the basic shape of an ellipsoid, I could do something like this. I could create an ellipsoid with some kind of X and Y radii here. And then I could create another ellipse in the Y and Z plane. And then the X direction of the ellipse has to be the Y value. So that's going to be this one. And then the Y direction has to be the Z value. So this way I am creating, okay. And then you can see how the two ellipses are now matching here in the kinks, in these intersections. And then for the XZ plane, I can drop another ellipse. And then the X direction is going to be the X value here. And then the Y direction is going to be the Z value here. And you can see how now these three are could be the generative lines for an ellipsoid. So this kind of like bean shape object in 3D. All right. This is by combining ellipses in 3 different orientations in 3D space. All right, I'm going to save this. explain two planes. Okay. Now, planes can also be just created from scratch. They can be created from all their original components. So if I choose to construct a plane from scratch, then what the component is going to ask me is for the origin of the plane as a point. It's going to ask me for an x direction as a vector and a y direction as a vector. I could I could construct a point and I could construct two vectors with like 9 sliders, etc., but it's a little tedious. So I'm just going to take a little bit of a shortcut. So I'm going to drop here 3 points. I'm going to bring them into Grasshopper. So I'm going to set 1 point here at the center, the first one, and then I'm going to copy and paste this 3 times. The second one is going to be this one, and the third one is going to be this one here. All right. And then what I'm going to do is I'm going to use this point for the origin. Okay, so I'm just going to plug it in here. And by default, it's giving me a plane that is oriented in the X and Y orientation with the center here. I'm going to move this a little bit up in C so that we can see like volumetrically this plane having some kind of orientation. All right. And then what I'm going to do is I'm going to, instead of numerically generating X and Y, what I'm going to do is I'm going to create 2 vectors from this point to this point and another one from this point to this point. And then I'm going to use those 2 vectors to feed them into constructing the plane. How am I going to do that? We know this from the previous video. I can create a vector between 2 points. So that's going to be vector between the origin point and the first direction point, and another vector between the origin point and the second orientation point. If I wanted to visualize those, I could do something like this, where I could display from this anchor this vector, and I could display from that anchor the other vector. So I have those 2 vectors, which are the vectors that I want to use to align the plane. So now I just feed the first orientation vector, I feed it as the x vector, and I take the second orientation, but you see that, so now it is working, x is aligned with this vector, but you can see that this other vector is off plane. So I can plug in the second vector, and now you can see that the plane is contained in containing the second vector. But wait, Jose, well, this was very strange. You told us that vectors for planes have to be unit and have to be perpendicular to each other. They have to form 90 degrees between them. And these 2 vectors are clearly longer than 1 unit. 1 unit is this. Sorry, 1 unit is this. And they clearly don't form 90 degrees. They form something like, what is that, 70? So how could this happen? Well, it turns out that this component here is very smart. And what it does is it forms a plane with whatever, it forms the best plane that fits the information that it was given. For the origin, it can take it as it is. But if you give it an x vector that is longer than unit or shorter, it will resize it to create a vector, that is unit. That's one thing. And for the third vector, if it is not perfectly at 90 degrees, what it will do, it will use that second vector to just orient the plane so that it tries to fit that secondary direction as good as possible, but always respecting the 90-degree angles and the unit vector. So that's why this second vector is not aligned with this one, but the plane at least is containing the 2 vectors. So what we just did here, and the numerical and the numbers of how it's done are perhaps a more advanced topic. You can check my GSD videos if you want to learn more about that, or you can check some geometry gems. I think we've done some geometry gems to see that. But you can see that the plane is now represented with the x, y, z of the center, and here numerically it with the c vector. All right. Okay, so what we have done here is implicitly create a plane by finding the two vectors for direction and using the origin. So basically what we've done is create a plane using 3 points. Well, it turns out that in Grasshopper, there is a component that directly, without needing to find the intermediate vectors and blah, 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 it already gives us a plane using 3 points. The main point is going to be the origin. So that's going to be, I'm going to turn this off and this off so that it's clear what I'm doing. The first point is the origin. The second point is the orientation of the x. And the third point is the orientation of y. And if I do that, you can see that this plane is identical to the one that we manually generated. So this, in a way, is a shortcut. And are they identical? Let me plug it in here. Yes, they are pretty much identical. So this form here is like a manual way of creating planes where from 3 points, where this was basically using a shortcut, using a component that does that automatically for us. Mm. And I'm just going to close this, yes. Okay, what is next? I'm going to talk about doing a curve, and the curve is, we can divide in perpendicular frames. Now, of course, we're not even close to being done here, because now is when the cool stuff start. So remember in my previous video when we were doing vectors, we discussed how we could divide a curve into a series of points, and the component gave us additionally, as a bonus, it gave us the the tangent direction at the curve on those points. So very similarly, we can find, for example, for a curve, we can find planes that define the orientation of that curve at each one of those division points. So for example, if I have a curve that is on Rhino and then I bring it into Grasshopper, then something that I can do is I can go to curve and I can go to division, and then I can divide a curve in a set of frames that are perpendicular to that curve along the curve. So if I do that, I can say now I can divide that curve and you can see all those planes, and then I can, for example, I can make, oh, sorry, no, this should be an integer. So I can say, I can subdivide in 20 amounts of points. And this is something that is going to happen very often. Sometimes the size of the planes, how they are rendered inside of Grasshopper, it's a little too big, or sometimes it's a little too small. So something you may want to play with is going to display, preview plane size. Here you can change the size of how big planes show up on your screen. So for example, I'm going to reduce it to number 2, and you can see that now the planes are much smaller, and you can see how super cool each one of these planes is now defining perpendicularity to the curve along it's along its twisting, right? And you can see the x and the y directions of the plane. So this can be really useful, for example, now to draw ellipses that are oriented there. And for example, these are going to be the x and the y, right? And you can see how, for example, I can have one dimension that is really dominant over the other, and then you can see how these ellipses are now oriented according to the perpendicularity of the curve. So if we wanted to, for example, create an extrusion of a profile across this curve, we could just say, let's create a loft, for example. Let's create a loft that is going through all these curves that I have generated. And then I can have this elliptical section kind of pipe that is going through all those perpendicular frames that I just created. And what's interesting also is that the orientation of these planes uses the tangency and the curvature of the curve as the main directions. This is what's called binomial planes. I forget binomial, binomial, I think it's called binomial planes. Let me double check that. I don't want to lie to you. Yes, sorry, I was actually lying to you. I brought binomial because I was recently studying it, but it's not the binomial plane. It's called the osculating plane. It's a plane that is formed by the tangent vector as the main direction, and is formed by the radius of curvature at that point on the curve. So that's what is happening here, and so the C is the tangent, and x is the center of curvature. Is pointing towards the center of curvature in this curve. This was unnecessary information, but still cool though. But yes, so we can use this, for example, to orient geometry, to orient curves on top of other curves according to perpendicularity and according to tangency. But this, of course, is not reduced to curves only, it's also applicable to surfaces. Okay, so now let's draw a surface. I feel like I always draw the exact same surface. The exact same kind of geometry, and then on left from here to here, and okay, and then I'm going to draw this curve. So for example, let's say that I have a surface in Rhino that I bring into Grasshopper. And what I want to do is I want to now populate on top of this surface a bunch of geometry. And hopefully what I want to do is I want to make sure that that geometry is respecting or is oriented somehow according to the curvature of the surface. So what we have learned in the previous exercises is that I can subdivide a surface in a bunch of points, for example. And if I press here, if I add here a couple of UV parameters, I can subdivide this surface into a collection of U and V points. And then let's say that I wanted to use those points as the center to place cubes, and those cubes be oriented towards the surface. The way I would do that is, for example, I would go now to primitives, I would go to center box, and I would create a box that is centered on a plane. Ha ha ha. So you can see that the input for this component, for this box, is going to be a base plane. However, I don't really have base planes. The only thing that I have here is division points. So I can still plug it in here. And actually this is a little too big, so let me reduce the size of these elements. So X and Y and Z. So I'm just going to make those smaller, okay? So now you can see that these cubes are kind of showing up there, but first of all, they're not oriented along the surface. But also, what happened here is that I had points as geometry that I plugged into a plane input. Why does that even work? Well, it works because since planes and points are kind of very affine, very similar types of entities, you can think of points as a dumber or a simpler kind of entity that a plane. A plane has so much more information. It has a point, which is the origin, but then it also has two direction vectors. Whereas the point is just a location in space. So what Grasshopper does in this case is that whenever you give any input, you give it a geometry type that is simpler than the geometry type that it can actually take, then what it does is it adds on top of the missing information some default information. In this case, what is happening here is that to the points, this component takes those points as the origin of the planes that it's going to be using to orient these cubes, but it gives those planes default X and Y directions in the X and Y world coordinates. And that's why all these boxes are actually oriented in the X and Y coordinates of the world. Now, this is not really cool. So what I would like to do is I would like to make sure that these boxes are oriented along the surface. So maybe I could do some operations with the normal vectors and play around with that and see if I could create planes that respect that orientation. But actually, I'm going to save us a little bit of that, that processing. Actually, if I go to utils, you can see that the divide surface component, this one, is right next to another one that is called surface frames, which says that it generates a grid of UV frames, so UV planes, on top of a surface. So this component is basically the exact same thing. It's just that instead of giving us points and normals, it gives us planes. So I'm just going to plug in here and in here and in here. I'm going to make this surface like, I'm going to scale it by a factor of 3. So I'm going to scale it. This surface base point is going to be 0, 0, 0, and then the factor is going to be 3. Okay, so now much bigger. You can see that the planes that I'm getting from that subdivision are actually aligned very nicely with the surface. So now if I use those planes to orient these cubes, now the cubes are not going to be aligned with XY, I'm going to be aligned with the surface now. So you can see how nice these cubes are respecting the orientation of the surface. They are really nicely aligned. And if I actually play a little bit with this, if I wanted to extrude them farther in the x direction, I could overlap. I could change the x, and you could see how now they are creating this super nice form sticking out perpendicularly from the surface. This is really, really useful for a lot of operations. You see how nice this is? Huh? So this is why, for example, I have stopped using divide surfaces like in forever. Because like if I can generate more and better information, why not? Right? Because like this is similar to what I was saying from when I was talking about grafting, flattening, and I said that as much as you can, try to use graft so that you always stay at a higher level of information and you have as much information as possible. If your computer is not lagging, etc., etc., if you can keep up with that. But if you have planes, planes contain points inside of them, but they also give you orientation. They also give you the two vectors. So why would you want to work with points only if you can work with planes and at any time just extract the point if you only need that point and cut away the information? All right, so it's the same principle. So this is how to use planes to orient, for example, geometry on top of a surface. Mm. All right, so bottom line, this is what I wanted to say about planes. It's going to, again, I would like to do some hands-on exercise to practice and to see how they can be useful in other scenarios. But long story short, planes are one of my favorite entities when it comes to working in 3D. They have like a lot of information. They're super useful. They keep orientation. It's great. It's, for me, they are the MVP and they're super cool. So I would recommend that as much as you can, you work with 3D planes as the basis of your geometry generation and manipulation for the reasons that I just explained here and for other reasons that we will see very soon farther down in this sequence of videos. All right. So until then, this was Jose Luis, this was planes, this was intro to parametric modeling. Thanks a lot. If you like what you saw, maybe consider subscribing to this channel, liking this video, turning on notifications and all those things. And I will see you on the next video where I think I'm going to be talking about numerical series. All right, let's take a look at that. See you on the next video. Thank you. All right. Okay. Oh, how's everyone doing? I'm kind of tired. Where's my water? Ugh. Here. All right. Oi. Ooh. Ay. What's going on? Okay. All right. Okay, so what are we doing next? What are we doing next? We're doing numerical series. I think, am I stopping? I'm not stopping. Let's, I'm probably gonna stay it for another 30 minutes, 45 minutes, another couple videos. another 1 or 2 videos. So let's save this. Let's save this. Let's save this. New exercise. Okay, and then this one is going to be saved, and it's going to be new one, no template, and numerical series. Okay. Okay, and I'm going to save this. Do I need to do any diagrams here? I don't think so, right? I don't think so. Okay. How am I going to start this video? How are we going to do this? How are we going to start the video? I'm going to say that we have seen planes and vectors, etc., but they're basically collections of numbers if you see very abstract. So very often the way we generate them is creating numerical series, and that's an interesting way of creating them. I can do a couple numerical series that is a one grid. I can use that to generate 1D points. I can generate 2D points. I see. And I can generate 1D points. Okay, so let's do that. I think we're going to generate 1D point series linear sine radial. Okay, we can do that. Okay. And we're going to drop here some bifocals. Okay. Actually, am I going to point to the other video? DSD. Oh no. This one. Oh, the audio was terrible in this. The exception will be the audio was terrible. This was the second video we recorded. We were still trying things out. Okay, and can I get the playlist view? Can I get the playlist view? Yes, datum data. I would like that video better. All right. I can't believe this was a year and a half ago already. Time flies. Okay. All right, let's do this. Hi, this is Jose Luis, and welcome to another video on the series Introduction to Parametric Modeling. In my previous videos, I have discussed how to create and modify vectors and how to work with planes. But if you think about them in a super abstract way, what they basically are is just collections of numbers. Point and vectors are 3 numbers, if you have them in 3D space, and then planes are basically 9 numbers, the numbers that define the origin and the 2 vectors that define the orientation. So it turns out that numerically they are very simple to represent, and it turns out that in order to generate sequences of points, of vectors, and of planes as well, it is actually very handy to get a grasp on how to generate series of numbers. So in this video, what I would like to teach you is how to generate a complex series of numbers using Grasshopper, for example. And we're going to see 3 main things. We're going to see how to create domains, how to create series, and how to create ranges. What does that look like? Well, we're going to start with domains. We've actually seen this in a previous video, but if you go to mathematics and if you go to domain, you can see that there is this entire category that is about domains. Domains in Grasshopper world is basically an interval defined by a starting value and an ending value. It's just as simple as that. It's 2 numbers that define a start and an end. And this is very useful because sometimes when we create geometry, for example, the size of a rectangle or the diameter of the size of a cube, instead of defining it in size terms, we define it in domain terms so that the object can be offset from the center point. We've seen this before. Constructing a domain is just as simple as giving it a starting point and an end point. So for example, I'm going to drop here a slider that starts at 10, but I'm going to right click and I'm going to make sure that the starting value is -10 so that I can have positive and negative values. So I'm going to call this start, and then I'm going to copy and paste this and I'm going to call this the end. All right. So this domain is going to start, for example, in -10 and it's going to end at +10. And if I plug in here, a panel, you can see that what it says here is that this object that is coming out of here is a domain that starts at minus whatever or positive whatever to the other value. So -10 to +10. All right. You will see very often in Grasshopper components that ask you for domains. So for example, as I said, if we want to create a rectangle, what is the rectangle? You can see that the rectangle in the x direction is asking for the dimensions as a domain so that it knows how to offset or how to center this object in the plane that is the base for the rectangle. All right, so this is just a simple domain, and sometimes it's called an interval, and the 2 numerical extremes that define this domain. But I may actually want to generate more complex series of numbers. I may want to create sequences of numbers that start at a particular value, that end at a particular value, or that have a particular amount of numbers and a particular distance between them. This is also very useful. It will be very useful, for example, for creating, I don't know, sequences of points in 3D space, which I think is an example that we're going to do in this video. So for example, let's say that I go to the Sets tab and I click on Sequence. If I click on Sequence, you can see that there is a component here that is called series, and it's useful for creating a series of numbers, just as simple as that. The inputs are going to be S, the starting number, N, the step size, and then C is going to be the number of values in the series. So I'm going to copy this, and I'm going to say this is the starting value, which I'm going to set at 0. I'm going to copy this, and this is going to be the step size. And then this C is going to be the number of values. This has to be an integer. So I'm just going to say, for example, 25 values or 10. And then, for example, if I click here, number 1, and then I type count, and this is going to be C, then what you can see is that the output is a list of numbers that starts with the starting value. You see? The step size is 1 unit, and there are 10 numbers on this list. I can choose to have more or less values. I can choose to change the starting value, and I can choose to increase the step size or to decrease the step size. The step size being the interval, the gap between these numbers. So numeric series in Grasshopper is a way of creating series if you know what is the starting value and if you know what is the step between values. All right, this is very important. And it's very important because it's different from the other way that we have in Grasshopper of creating numerical series, which is using ranges. Ranges is a very, very similar concept, but it's slightly different in that instead of defining the beginning and the step size between values, what we define is the beginning, the end, using a domain, and then we define how many intervals we want in between. So for example, let's say that I choose to start at, let's say that I look at the value, I look at the range, sorry, and you see that the input is asking me for a domain. So it's asking me if I want values between -10 and +10 in this case. And N is asking me for the number of steps between values, which is going to be also something. So for example, here, I'm going to rename this to steps. And then I'm going to plug this in here, and you're going to see that the result of this is going to be this much. So it's a sequence of points that go from -10 to +10, and there are 10 steps in this series. All right? Now, I want to highlight one thing that is typically a little confusing, but that we need to wrap our heads around. Let's say that I said that the starting value was going to be the value of 0, the end value, the value of 10, and 10 steps on the series. Look at, which is basically trying to mimic what I did here with the series. What's interesting is that if I compare the results, it turns out that the range is giving me one more value than the series. And it is so because what I get with range is that the number of, what the input that is asking me for is the number of steps, as opposed to series, which is asking me for the number of values in the series. If I divide a domain, for example, in 2 steps, then what I get is 3 numbers, the beginning, the middle, and the end. If I divide it in 3 steps, I get 4 numbers. If I divide it in 10 steps, I get 11 values, which is what I have here. Because remember, index numbers, I start counting with 0. So 10 as the last one means there's 11 values. So keep in mind that when we use series, we want the amount of numbers of values, whereas when we use range, we specify the amount of steps in between the values. And therefore, the amount of values will be the amount of steps plus 1. Okay, let's keep that in mind. Ooh. So now let's create a bunch of points. No? Is that what we want to do? Let's create a series of points with this technique. All right. So I'm going to save this as 6.3. Uh-oh. All right. And now, why is this useful, Jose? This is kind of boring. We're just generating numbers after the other, right? Duh. Well, it turns out that having this fine control on the generation of our numerical series is actually really helpful whenever we want to use this information to generate sequences of geometry as well. So for example, let's see a really simple example of how to generate a 1D, one dimension array of points. So like a sequence of points, one after the other. So the way we have seen how to generate points in the past has been using the construct point, okay? And the way we typically did that was by saying, I'm going to work with the coordinate x, the coordinate, and then the coordinate y, and the coordinate z. Okay? And that gives us a point that we can use to control in 3D. All right? But what if instead of just plugging in here one single value, what if we plugged in a list of values? How would that work? Well, let's see if we can make that happen. So I'm going to copy paste this series. Okay. I'm going to bring it all the way down here. And then what I'm going to do is that the x coordinate, I'm going to detach it. So I'm going to right click on the component here. We haven't seen this yet. And I'm going to, well, you can't see it, sorry. I'm going to right click and I'm going to disconnect the first slider that is coming in. So that slider there. And then what I'm going to do is I'm going to, because I like visualizing things, I'm going to make sure that I have a panel here. So instead of plugging in just one number for the x, what I'm going to do is I'm going to plug in a series of numbers. And then what happens is that, remember, the component works when components combine data. What they do is that they perform every operation by matching objects one to one. So what we get in result is a collection of points that have all these x, y, all these x components, the series, and then the y and the z are the same, which are these hard-coded values. If instead of x, I wanted to do that in the y direction, I could just plug this one in here and then plug this one in here, and now the points are going in the y direction. Or if I wanted to do that in the, I wanted to do that here in the z direction, so now the points are going up. Okay? So now I can generate one-dimensional series of points. Now this is kind of interesting because then it opens up the possibility for a lot of creativity. Because, for example, what if instead of having these points just be boring, like, just instead of being boring a straight line, what if I wanted to do something a bit more creative? Something I could do, for example, is I could create a series of points that is kind of undulating like this. The way I can do that is by by working with these points and then giving them an x coordinate that is growing in this direction, but then give them a z coordinate that is undulating and is oscillating between the values of 0, 1, and -1. I can do that with a sine function. So for example, let's say that I'm going to change my series, or I'm going to create a new series instead. Okay, it's going to start, or I'm going to do it with a range instead. Actually, now that we're talking about it, I'm going to copy this range. Okay, and I'm going to say that the range needs to start at 0. The range needs to end at 307 needs to end at 720, which is 2 times 360, so 2 iterations. And then the amount of steps is going to be 1 minus the count here. So that's going to be subtraction. So that's going to be 10 minus 1. And I'm going to hard code that so that the numbers match. So this is minus 1, and then this is going to be here. So what I have done here now is I have created 10 numbers. Sorry, it's minus 1, so it has to be positive 1. So I have created 10 values that go from 0 to 300 to 720. If I use those values now as the z coordinate, you can see that what I get is like this really sharp straight line that is like slightly inclined. But what I want to do is I want to make sure that instead of that, what I want to do is I want to use that to create some kind of like undulating effect. So what I can do is I can calculate the sine of this value. So I can go to mathematics, trigonometry, and calculate the sine of this value. And if I do that, I can plug this in here, and then I'm going to get very strange results like these ones, just because the sine function by default works with radians, and here I'm working with degrees. So there's actually a function here that takes an angle specified in radians and turns it into degrees. Or, so I could do that, and now I have actually the other way around. I have to turn the angles in degrees into radians. So I can do that, and now my angles are specified in radians, so 4 pi. And then if I feed that to the sine, you can see that now it's a little better because it's 0, blah, 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 and then it oscillates back into 0. And then if I plug that into C, you can see that I start getting this kind of undulating effect. If I crank the count of points up, so you will be able to see that I get a much nicer definition. You see, I get a much nicer definition, and I can squeeze that in here, and I get this like nice undulating curve, which it is made out of points. It's just a sequence of points. And you can see how here I have all the points from -1 to 1, all the c coordinates. All these points, I can use them to create, for example, an interpolated curve. All right. And this interpolated curve, if I turn off the points, is roughly following the shape of a sine function, as you can see, which is also kind of nice. Woohoo! Should I create a radial? Should I create a radial? I think I should do that. But if I do that, am I going to have to explain with the diagram? I probably want to explain something with the diagram, right? I probably want to explain that with a diagram. That was actually not a terrible circle. It looks really bad, but I thought it was going to be worse. Ooh, let me try again. I can do better than that. Wait. Can I do better? Is that true? Huh. Is that a little better? Wait, drawing circles is hard, man. Okay. All right, so that one is gone. All right. And then I can use this to draw. And then I'm going to draw. I'm going to draw this one, this one, this one, this one, this one. Now, something that I can also do, for example, is I can use numerical series to create a circle, to create a circle of points, right? How does that work? Well, if I want to create a circle that ends up in a circle, what I need to do is basically I want to be able to create a series where what I want to do is I want to be able to say I'm going to create a series where I'm going to start with this angle and then this angle and then this angle and then this angle. And for each value of these angles, I need to find the x and y coordinate of this point. And it turns out that if you refresh a little bit of your trigonometry, I'm not going to do it right now here, but I might do it in some other video. If you refresh a little bit of your trigonometry, you can see that this forms a triangle that is a square here that has 90 degrees. And then the x coordinate of this point equals this distance. And with trigonometry, we know that the x coordinate is going to be equal to the radius, which is going to be this one here, times the cosine of the angle, which is going to be this one here. And so that's going to be x. And we also know that the coordinate y, if you refresh a little bit of your trigonometry again, we know that the coordinate of y is going to be the radius, which is that distance, times the sine of the angle that we are forming there. So if I create a series of angles that go from 0 to 360, and I can use that to compute the x and the y, and then use those two values to compute the circle. All right, let's take a look at how to do that. So I'm going to go back here, and I'm going to create a similar like this. I'm going to create a range that is going to go from 0 to 360, and it's going to have how many steps? It's going to have 12 steps or 24 steps, for example. So that's going to be this many. And let's take a look at the values here. So I have 0, 15, 30, blah, 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 all the way down to 360. As you can see, I'm not a great fan of radians. I like working with degrees for some reason, and they're just a little more intuitive to myself. Okay, and then for this one, for each one of these, I can just do some simple arithmetic. First of all, let me set up the radius. So the radius is going to be a parameter here, and I'm going to set it at, for example, 10 units. And then what I'm going to do is, of course, I'm going to use expressions. So I'm going to other expression here, and I'm going to take, for example, the angle, and this is going to be this thing here, and I'm going to take the radius as well as an input. So I'm going to take the radius, I'm going to plug it in here, and then this is going to be equal to the radius times the, what is the cosine? The cosine is cos, all right? So cosine of the angle. So that's going to be one thing. And the other one is going to be that this is going to be times the sine of the angle. But I forgot to convert the angle into radians. So I need to do that. For example, I'm going to do this here. I'm going to say that this has to be radians, and then that is what I'm going to plug into the angle. Okay, the radians are going to be here, 0, half pi, pi, 1.5, and 2 pi. Have I ever told you how I don't believe in pi? That I'm a Taoist? But I think you can actually Google that. So I won't get into that right now, okay? So I have this, and then what I can do is I can use these as the coordinates of the points. So I'm going to construct a point with this x, and you can see that this is like a squished circle right now, and with this y, and then c is going to be 0 for all of them. Okay, so that's how I would create a circle out of points. But wait, can we make this a little more exciting? What if instead of a circle we make a spiral? Can we do a spiral? Well, a spiral, instead of instead of z being constant, what we can do is we can make c a value that increases, for example, linearly. So is, for example, let's say that I'm going to create a series that is going to start at 0. The step size is going to be 1 unit, and the count is going to be 25. I'm just going to do this manually, but you could do this, for example. Let's not do this manually, because I cannot preach things and then not do them myself. So if the steps are 24, then we need one more value here. So this should be the addition of 24 plus, the shortcut to put in a panel is 2 forward slashes. And then I can just write in here the number 1, and it will give me a panel directly with the value of 1. And then I'm going to plug that in here. So that now I have a series of numbers that start at 0, have the step size of 1, and then let's take a look at that. 0, 1, 2, all the way to 24, and then I'm going to use those to plug into the C coordinate. And then you can see I am getting a nice spiral in 3D. But wait, it's just one thingy with a spiral. Can I make the spiral like at least have a couple loops? Yes. So instead of starting at 0 and 360, I can just crank it up to 720, for example. And now I have 2 twists. And then look at this. How nice is this? Yo! All right, because the size is the same. Okie dokie. So that could be one thing. And also, wait, but the radius is kind of like a cylinder of a spiral. Do we think, let's double this so that we have a little bit of more definition. What if we actually did something where instead of a cylinder spiral, was kind of like a cone. It started with a very small radius, and it increased that radius. Well, how do we do that? Well, instead of having the same radius for all the calculations here, we can have a radius. So instead of having the same radius for all the points, which creates a circle, if we start with a tiny radius and then we start incrementing the radius, we will basically be making a spiral in this direction. So that's why we still work with an increasing angle, but with the radius is a value that starts small and then it increases and increases and increases. How do we do that? With another series. So for example, let me say that the radius, where is my mouse? The radius, instead of being a number, just one number, is going to be a list of numbers. And so I'm going to actually copy and paste this series here. And the start is going to be 0. The step size is going to be something very small, like 0.1. And then it's going to have as many values as the steps plus 1, like we did here. And then I'm going to feed that into the radius here. And I'm going to feed that into the radius here. And then you can see now how on top it's a spiral. And the perspective here is this kind of like opening sort of cone of a spiral. I don't even know how to name this, but we can open up if we open up the step. So this can now like open up to be a bit more, and then we can just create an interpolated curve here and see this in kind of like in 3D kind of, and we could extrude something around it. We can do perpendicular planes, and we can just place ellipses, and we can do all the cool things. So let's just do that. No, we're going to place some ellipses here, you know, and then we're going to extrude that with a loft as well, and choo. Well, the loft is a little weird here, but but it's kind of I think actually the right one would be to do a sweep, with the rail being the curve and the section curves being these ones, right? I think this is a more accurate one. Yes. Okie dokie. Woohoo! So how cool is this, So we have been able to numerically define a curve by defining a sequence of points that hold some kind of relation between them. In this case, creating, for example, a spiral that is ascending in the z direction by just using simple trigonometry and like a sequence of numerical values. All right. Now, can we use this trick to generate, instead of sequences of points in one dimension or in one direction, can we do that in two directions? Like a grid of points? How will we go about that? All right, how will we do that? I think this is going to be the last video today because I'm a little brain dead and you folks have already taken a lot. How would we do that? Okay. Okay, so we're going to do this. There's going to be a panel here. going to create another series, which is going to be 5, and it's going to be 5 elements, for example. Well, it's actually going to be fairly easy. It's just that it's going to involve a little bit of data manipulation, the way we've seen in previous videos. So for example, I have created two numerical series. One goes from 0 to 9 in increments of 1. The other one goes from 0. The other one has 5 numbers from 0 with intervals of 1.5. I want these to be the x coordinates of a grid of points, and I want these to be the y coordinates of a grid of points. So how can I do that? Well, if we were to say, let me construct a point, and then for this point, let me add the x coordinates here, and let me add the y coordinates here. What would happen is that we run into a specific behavior of grasshopper components, which is that whenever a grasshopper component takes two different lists and needs to work with them together, what it does is, if the two lists have the same branch and the same name, what it does is it tries to combine the elements from one input and from the other input. It tries to combine them one by one at the list level. So for example, what's happening here is that the component is creating the first point with 0, 0, and a C value that I haven't really specified. That is the default, but it's going to be, for example, 0 for C, okay? And then the second one is going to take the value of 1 and the 1.5, value of 2 and value of 3, value of 3 and value of 4.5, value of 4 and value of 6, and that would be this point here. But then, because Grasshopper runs out of elements on this list to match with the previous one, it just sticks to the last one. So for 5, 6, 7, 8, and 9, it's going to pair those values with the last one here, with number 6. This kind of data matching is called longest list, because it basically creates element as long as the longest list, but it repeats the last one that it finds. So that's like the standard behavior for Grasshopper components. Now, this is not the behavior that I wanted. The behavior that I wanted was take coordinate 0 and then create one point for 0, for 1.5, for 3, forever, so that I have this point here, another, and then the second one, take coordinate 1, and then give me one point here, another one here, another one. So I want a two-dimensional grid. Because Grasshopper matches elements one by one if they belong to the same branch, then what I will need to do is that I will need to change the branches so that that one-to-one matching does not happen. So how is it going to work? Well, what I'm going to do is I'm going to open this up and I'm going to graft the tree that is coming from here, from the y coordinate. I could graph the other one, it doesn't really matter. The result of this is that I now have a data tree that looks something like this. I have 5 branches with new names. None of these names match the name of this branch, and therefore, because they are different names, a different behavior is going to happen. What's going to happen is that as I plug this here into y, now I get a two-dimensional grid, because what happens is, since they have different names, then what the component does is it takes the whole list and it matches the elements with each one of the other lists, one by one. So it takes this whole list and it creates one point for each one of these elements and for each one of the elements on this branch. And because there's only one, then we get this row of points. Now for coordinate 1.5, it matches it with all these points here. We get the second row. For 3, we get the third row. For 4, for the fourth row, etc., etc. All right. So this is how you would create manually, for example, a two-dimensional grid of points with a numerical series and doing a little bit of manipulation. Now, let's say that I wanted to control where the first point is. I just don't want the grid to be here, center, and 0, 0. Let's say that I have a reference point somewhere in Rhino that I want to use as the starting point. So what I can do is I can just say, I'm going to bring that point here. I'm going to set this point. And then what I'm going to do is just a very simple operation, which is going to be, I'm going to deconstruct this. I'm going to find the x, y, z coordinates. And then what I can do is I can either add these numbers to the x direction. So to x, I'm going to add, to the x coordinate, I'm going to add all of this. And to the y coordinate, I'm going to add all of this. And then I'm going to graph this. Right? And then what happens is that now the coordinates are, and now I'm going to add this, and now the coordinates are just added to the original coordinates. So if I move this here, now things are adapting correspondingly. Alternatively, I could have just done start the series from x and from y. That could have been another, just start the series instead of from 0, start from whatever the coordinate x and the coordinate y was. It's the same thing. Actually, this is a little easier and a little more elegant to my taste. Okay. Now, can I do the same for C? Let's see if we can do that. We can actually, full disclaimer, we're not going to be able to do that because I would want to say, well, maybe we can graph this and then I'm going to plug this in here, but then guess what happens? What happens is that now I get points kind of inclined like that, just because, let me add Z here. I get points inclined like that because the structure of this grafting here is identical to what it had here. So these ones get matched to 1 to 1. They don't get combined completely. So what if do I have to graft again? What if I graft again? If I graft again, we have the same problem. They get matched 1 to 1. So this is not going to work. I will teach you in the next exercises when we take a look at affine transformations, how we can use moving things around as a way of creating, for example, three-dimensional matrices as well. All right? But I think with this is where I wanted, this is as much as I wanted to talk about for numerical series and examples of how that is useful for creating, for example, sequences of points. We're going to use a lot of numerical series very soon in the practice exercises that we're going to do for this block of videos. Okay? And with that, I'm going to leave that there. And I'm going to move on to the next video where I think we're going to take a look at Euclidean transformations. So moving things in space, scaling them, rotating them, and that kind of stuff. Until then, thank you very much for being here. This was Jose Luis. If you like this video, consider pressing the button or maybe subscribing to the channel, even turning on notifications to know when we go live and when we publish new videos, etc., etc. If you will. Okay, it's nice. It helps us keep going. So until then, thank you very much and see you on the next video. Woohoo! And then this is going to be 6.3. Okay. And I think with that, I'm a little brain dead for today. How are you folks holding on? How is everyone doing now? And it's also super beautiful outside. And I'm here and the CPU, the fan is blowing. It's really hot in here. Bartulokumchu. Bartulokumchu. That is a really fun sounding name. Thanks to you, sir, or gal. or lady, I'm not sure. So thanks a lot. It was a pleasure. If you have any questions, I may be able to stick around for a minute or two. I don't have meetings today, thankfully. And I'm going to save this before I lose it. And okay. And Metzrat. Oh, I'm sorry, you just got here and we're about to shut down because I've been streaming for 3 hours now and I'm kind of a little brain dead. And I want to go out and see the sun. That would be nice. I haven't had a lot of sun lately. All right. So if there aren't any questions or comments, thank you very much. I appreciate. Oh, thank you, Merat. Thank you very much. I appreciate that. So thanks a lot. It was a pleasure to do this in the company of human beings. And I will see you tomorrow. What is it today? Today was Thursday, so I'll see you tomorrow at 10 a.m. Eastern Time. And we're going to do 2 live streams tomorrow. I'm going to wrap up Euclidean transformations, and then I'm going to do a bunch of exercises to practice all these techniques. That is going to be quite cool, actually. And then hopefully we will jump on to learning about lists, which I'm not sure we'll have time to do tomorrow, but if not, we will just do it next week. It's fine. Thank you very much. It was a huge pleasure. See you tomorrow, hopefully. Otherwise, see you some other time. Bye-bye. Thank you.